Video, we're going to talk about a property that some topological spaces have, which is being Hausdorff. So we saw in metric spaces, a sequence can converge to at most one point. That sort of goes with our intuition about convergent sequences, whereas in topological spaces, this is not generally guaranteed. So for example, we saw that in the real numbers with the finite complement topology, that's where the set of open sets is the empty set union together with any subset A, subset of, in this case, the real numbers, such that A complement is finite. We saw that in that topological space, say the sequence 1 over n, from n goes from 1 to infinity, converges to pi. 1 over n also converges to negative 512. This sequence can converge to any real number in the finite complement topology. So it is not the case in a topological space in general that a sequence can converge to at most one point. So if we sort of want to think about topological spaces that do have this property, that a sequence can converge to at most one point, what more general property might prevent this from occurring and also sort of keep some other ideas of our intuition in check? So here is a definition that does just that. A topological space X tau is a Hausdorff space if for each pair of points A not equal to B in X, there exist disjoint open sets U and V such that A is in U and B is in V. So in other words, if A and B are not equal to each other, there's some open set U and some open set V such that U intersect V is the empty set, such that they are disjoint sets. For example, any metric space is a Hausdorff space. So, if we're talking about some metric space XD and X is not equal to Y, then the distance between X and Y must be greater than 0. Let's say that the distance between X and Y is equal to some number epsilon, which is greater than 0. Then the ball centered at X of radius epsilon over 2 and the ball centered at Y of radius epsilon over 2 are disjoint. They have no elements in common, and they are both open sets containing X and Y. So yes, that tells us that any metric space is a Hausdorff space. Here's an example of something that is not a Hausdorff space. The integers with the finite complement topology we described above. Now it's just on the integers instead. So the open sets in this topology are the empty set as well as any subset of the integers such that A complement is finite. This is not a Hausdorff space. Let's see that that is the case. So let's let A and B be integers. And let's suppose that U is open, contains A, and V is open and contains B. So these are both non-empty open sets. Therefore, U complement is finite and V complement is finite as well. So could it be the case that U intersect V is the empty set, that these two sets are disjoint? Well, if so, then let's think about the complement of them. So U intersect V complement would have to be the whole remaining set of integers because there's nothing in their intersection. And that tells us then, by De Morgan's laws, that then U complement union V complement is the entire set of integers. So that's just De Morgan's laws, flipping the intersection to union when we take the complements separately. But U complement and V complement are both finite because they are both open in this topological space. And So we have then that U complement union V complement is finite and also equal to the integers, and this is a contradiction. So it is not possible for two integers that are not equal, we should have said that, two integers a and b in the integers that are not equal, such that to have open sets u and v containing them, such that their intersection is empty, such that those open sets are disjoint. And therefore, the integers with the finite complement topology is not a Hausdorff space. Let's now prove that it is the case that in a Hausdorff space, a sequence can converge to at most one point. So let's suppose for contradiction that x tau is a Hausdorff space, and that there's some sequence xn that converges to A that also converges to some point B where A and B are not equal. Then since this space x tau is Hausdorff, that means that there must exist open sets U and V such that A is in U and B is in V, and the intersection of U and V is the empty set. However, since xn converges to A, there is some natural number, let's call it n1, such that for n greater than n1, x sub n is an element of U, since xn converges to A and A is an element of U that is open. And similarly, there is some n2 such that for n greater than n2, x sub n is in V, since xn converges to B, and B is an element of V. So for n greater than the max of n1 and n2, that means that xn must be an element of U and V. But this is a contradiction because U intersect V is the empty set. So yes, it is the case that if x tau is a Hausdorff space, then any sequence cannot converge to more than one point. Being Hausdorff is both a topological property and a hereditary property. So being a topological property means that if there's a homeomorphism between two topological spaces, then if one space has the property, the other space must have it as well. It's also a hereditary property, meaning that if the original space has the property, any subspace must also have it. So this is the proof of this is in the book. Let's do this one quickly, showing that that being Hausdorff is a hereditary property. So suppose that x tau is Hausdorff, and that A tau prime is a subspace of x tau. Let's let A and B be elements of A, where A and B are not equal. So then, since x tau is Hausdorff, that means that there exist some open sets. There exist open sets U and V such that A is in U, B is in V, and U intersect V is empty. Then let's just look at U intersect A. That's open in the subspace A tau prime. That's the definition of being open in the subspace. And similarly, V intersect A is open in the subspace A tau prime. And since U intersect V is the empty set, it's also the case that U intersect A intersected with U intersect, or intersected with V intersect A is the empty set as well. And since A is in U and A is in A, That means that A is an element of this open set, U intersect A open, and similarly, B is in V intersect A, which is open. So we have open sets in this topological space that contain the 2 points and are disjoint from each other. Therefore, A tau prime is Hausdorff.